A steel wheel on a steel rail has almost no grip, less than a car tire on ice. At 320 kilometers per hour, Japan's Shinkansen should slide off the track on every single curve. That's not an exaggeration. That's basic physics. So why doesn't it? The answer isn't one thing. It's a system of interlocking engineering decisions, each one solving a problem the previous one created. And if any single layer fails at speed, the consequences are measured in milliseconds. To understand how a 700-ton train stays on the rails at 320 kilometers per hour, you need to start with the rails themselves. Because the first assumption to correct is that the Shinkansen runs on normal train tracks. It doesn't. The Shinkansen runs on its own dedicated infrastructure, built from the ground up for one purpose: sustained high speed. When Japan launched the first bullet train in 1964 on the Tokaido Shinkansen line between Tokyo and Osaka, they didn't upgrade existing rail. They couldn't. Japan's conventional rail network used narrow-gauge track, 1,067 millimeters wide. That gauge was fine for slower regional trains. But at high speed, narrow gauge creates stability problems. The wheels are too close together. The center of gravity sits too high relative to the track width. So the Shinkansen was built on standard gauge, 1,435 millimeters. That wider stance lowers the effective center of gravity and gives the train a more stable platform at speed. But gauge width is just the beginning. The real enemy at 320 kilometers per hour is geometry. Every curve, every joint, every millimeter of track irregularity becomes amplified at speed. A bump that's barely noticeable at 80 kilometers per hour becomes a violent lateral shock at 300. So Shinkansen tracks are built to tolerances that would surprise most engineers. Cross-level accuracy is held to plus or minus 1 millimeter. Alignment over a 10-meter chord, plus or minus 2 millimeters. That's not a guideline. That's the operational standard. If the track drifts beyond those numbers, trains slow down until maintenance crews correct it. And maintaining that precision is why the Shinkansen increasingly uses slab track instead of traditional ballasted track. On a ballasted line, crushed stone sits beneath the rails and absorbs vibration. It works. But over time, the ballast shifts. Stones settle unevenly. The geometry drifts. At conventional speeds, you correct it periodically. At Shinkansen speeds, you can't afford the drift. Slab track solves this. Precast reinforced concrete slabs, each one roughly 4,900 millimeters long, 2,200 millimeters wide, and weighing approximately 5 tons, sit on a concrete roadbed with a layer of cement asphalt mortar between them. Circular concrete upstands, 400 to 520 millimeters in diameter, lock each slab in place every 5 meters, preventing any lateral or longitudinal movement. The result is a track surface that holds its geometry for decades with minimal maintenance. On the Sanyo Shinkansen, slab track maintenance costs run roughly 1/4 of what ballasted track requires. Now, even on perfectly aligned track, there's a physics problem you can't build away. Centrifugal force. When a train enters a curve at speed, momentum wants to push it to the outside. The faster the train, the stronger that outward push. On a straight track, the forces balance. On a curve, they don't. The standard engineering solution is superelevation, also called cant. You raise the outer rail higher than the inner rail, banking the track like a racetrack. Gravity pulls the train inward, partially counteracting centrifugal force. The Tokaido Shinkansen uses cant throughout its curved sections. But cant has a limit. Bank the track too steeply, and a slow or stopped train slides inward. You have to balance the needs of high-speed trains against the reality that maintenance vehicles, slower services, and emergency stops all use the same track. So the cant is set conservatively, and that means at full operating speed, centrifugal force still exceeds what the track banking alone can cancel. The remaining uncompensated force is called cant deficiency, and this is where the Shinkansen's most elegant piece of engineering enters the picture. The N700 series Shinkansen, introduced in 2007, was designed specifically to solve this problem, and it does it with air. The train uses an active body tilting system built into its secondary suspension. Inside the bogie, air springs sit between the wheel assemblies and the passenger car body. These aren't passive shock absorbers, they're actively controlled. When the train's automatic train control system detects an approaching curve, using precise GPS-calibrated position data, it sends a digital signal simultaneously to all 16 cars in the train set. The system adjusts the internal air pressure in the left and right springs differently. One side inflates slightly, the other deflates. The car body tilts inward by approximately 1 degree. 1 degree sounds trivial. It isn't. That single degree of tilt reduces the lateral acceleration passengers feel by enough to allow the N700 to negotiate 2,500-meter radius curves at 270 kilometers per hour, roughly 20 kilometers per hour faster than earlier Shinkansen models that lacked the system. On the Tokaido Shinkansen, where curves designed in the 1950s and 1960s are locked into the landscape between mountains and cities, that 20 kilometers per hour gain across dozens of curves adds up. It shaved minutes off the Tokyo to Osaka journey without rebuilding a single meter of track. The beauty of this system is its simplicity. Full tilting trains, like Italy's Pendolino, use complex mechanical actuators and can tilt 6 to 8 degrees. They're effective, but they're heavy, expensive to maintain, and mechanically demanding. The Shinkansen approach is different. It doesn't try to cancel centrifugal force entirely. It just trims the peak, 1 degree. Achieved through air pressure alone. No hydraulic actuators, no heavy tilt mechanisms, fewer moving parts, higher reliability. And on a line that runs 13 train sets per hour at peak, reliability isn't optional. But the track and the tilt system assume one thing. The ground underneath stays still. In Japan, it doesn't. The country sits at the junction of 4 tectonic plates. Over 1,500 earthquakes are recorded every year. The Shinkansen network crosses directly over active fault lines. And at 320 kilometers per hour, a seismic wave can shift the rails faster than any driver could react. This is where the ticking clock becomes real. When an earthquake strikes, there are 2 types of seismic waves that matter. P waves arrive first. They're fast, compressional, and relatively weak. S waves follow. They're slower, but they carry the destructive lateral shaking that derails trains. The gap between them is usually just seconds, sometimes less. The entire Shinkansen earthquake defense is built around exploiting that gap. The system is called UREDES, Urgent Earthquake Detection and Alarm System. Seismometers are installed along the coastline, near fault lines, and along the Shinkansen corridors themselves. When a seismometer detects a P wave, the system doesn't wait for human confirmation. Within approximately 1 second of detecting the initial wave, it calculates the expected intensity and sends an automatic alarm. Power to the overhead catenary wires is cut instantly. Onboard systems detect the power loss and trigger emergency braking. The train begins decelerating before the destructive S waves even arrive. Experienced Shinkansen engineers have a saying about this system. The alarm doesn't prevent the earthquake. It buys you seconds. And at 320 kilometers per hour, seconds are everything. A train decelerating at emergency braking rates covers roughly 90 meters per second at full speed. Every second of warning translates to measurable distance. Slower speed at the moment of impact means lower derailment risk. Lower derailment risk means the difference between a survivable event and a catastrophe. The system was put to its ultimate test on October 23, 2004. A magnitude 6.8 earthquake struck the Chuetsu region of Niigata Prefecture. The Toki 325, a Joetsu Shinkansen service carrying 151 passengers, was traveling at approximately 200 kilometers per hour. The epicenter was so close that the UREDES system had almost no lead time. 8 of the train's 10 cars left the rails. This should have been a disaster. A 200 kilometers per hour derailment on elevated track during a major earthquake with passengers aboard. But no one was killed. No one was even seriously injured. And the reason goes back to decisions made years before the earthquake happened. JR East had independently identified active faults near the Joetsu Shinkansen route, even in areas the government hadn't designated as high risk. They reinforced approximately 3,000 viaduct piers along the line. The section where Toki 325 derailed was one of those reinforced sections. The elevated structure held. The train stayed on the viaduct. It didn't fall. A University of Tokyo professor who investigated the site later said that if the viaduct had collapsed, the train would have crashed, likely killing everyone aboard. After 2004, JR East installed L-shaped rail guides and anti-derailment devices along vulnerable sections. These don't prevent wheels from lifting off the rail, but they prevent the train from wandering laterally after derailment. They keep the cars aligned with the track structure even when the wheels are no longer on it. It's a last line of defense. And it exists because Japan treats every near miss as an engineering lesson, not a lucky outcome. The Shinkansen network has now carried over 10 billion passenger trips across 6 decades of operation. 0 passenger fatalities from a train accident. That record isn't built on a single technology. It's built on layers, track geometry measured to the millimeter, slab construction that holds its shape for decades, a tilt system that uses air pressure to buy 20 kilometers per hour on every curve, an earthquake warning network that trades milliseconds for survival, and a culture that reinforces viaduct piers against faults the government hasn't even flagged yet. It's not one system keeping the train on the rails. It's the refusal to trust any single system to do it alone. Have you ever wondered how airplanes actually land in 0 visibility? That process relies on a similar philosophy of layered precision. I've covered that in another video.